Thank you, everybody. It's a great pleasure to be here in the second time presenting in the CemFuels. So I want to thank you, Rob, and the whole team of Global Media for being very supportive and for having us. Also, I would like to thank Michael, because he not only supported the whole project that we are going to present here, but also when we invited him, he just promptly replied and accepted the challenge to come here and co-presenting with me. So thank you very much.
No problem. Thanks also for having me here. When I was asked to come and talk about the project we had with Joana, it was no problem at all. It's been over the last couple of years, but we've learned a lot with regard to kiln balls, and it is a big challenge to us. So thank you all for everyone for having me here. It's my first time presenting, so bear with me, please, and thank you.
So today we're going to talk about kiln balls, and it's one of the most complex issues that we have when talking about building apps and recirculation problems. And we had just a video in case.
It's looking better.
Alright.
Are you taking a video of that?
When you go here and help John, he's got me some help, but it's not going to do it himself.
I'm just hoping this freaking bowling doesn't tear this bird pipe out, man.
I'm coming.
Yeah, we're taking pictures with our phones because I don't know how to take a picture from this. This is crazy, man.
So, from the video there, guys, as you can see, there is a very large extent of kiln ball. It's been noted there at the burner pipe. From the video, it's not our own plant, but we have witnessed instances like this. So much so where it actually did take the burner pipe with it and it ended up in our cooler. So it can cause serious damage. So it is quite a problem for us in Kinnegad. We've learned to try and deal with it, but to understand it, this is what this whole project was about. Thank you. Just as a basic analysis tool where we first set off, as you can see from the basic AR versus SR table above, we have shown three plants there, plant B, BH and T. In general, looking at it, the best place to be is right in the middle. Okay, all plants are quite in the control process, but plant B has kiln balls out of both of them, and that plant B is Kinnegad Breedon Cement. As another tool that you can use is the SV sum. So in general, if you're over SV of 40, you are more prone to kiln ball formation. Our current plant, we're running close to 33. We are in a good place. It's just pretty much to highlight general things there, but you can still have kiln balls, and this is why we are trying to investigate to see what is the root cause behind them. Just a bit of a background behind the plant. So we're in production since 2001, 2002. From the day we start production in Kinnegad, we've always struggled with kiln balls. I suppose in the last 10 to 15 years, as our alternative fuel replacement has increased, they have become more prominent. There, over 3 months back in 2023, really when it started at the end of 2022, we had a lot of occurrence of kiln balls. So we decided to do a deep dive investigation and try and find and understand what are the main causes. Using Tom Lowe's and Trie's help, using AI analysis based on a parallel coordinate, we were able to identify our main process drivers. On that, the main ones were our calciner fuel combustion and how it was impacting in our kiln, driving up sulfur cycles CO linked to unstable kiln conditions. As a result, we were producing kiln balls from coating formation.
So they contacted us, and just to show our experience, this is one example of a plant in Australia we helped. They were burning high cal at that position, and then they could not achieve the burnout. They could not really burn the combustion material above 41% of burnout. Then we helped them to relocate, and they could achieve 99%. And it was like that. Oh, the kiln walls problem solved. Everybody's happy. And then 6 months later, I received a call. Oh, Joana, the kiln balls are back. We checked it. The fuse is still everything burning 100%, no combustion problem, but it seems that it did not solve the problem. Then we checked again, and then we found it was much more the chemistry related at that time. But I just put this in a small example just to give you the mood and to keep the main message, as we said in the beginning. Kiln balls are really tricky, and most of the time that we faced it and we helped customers with this, it was more a combination of combustion and the chemistry. So that's why it's not so easy to really find the root cause straightforward. So for Breedon and for many of the companies that we help, we do the modeling. And just to explain a bit better, for this type of complex problems, we use not only the CFD, but we have our own tool, which is the Trie Smart Flow. And the difference is it calculates everything that CFD calculates, but we combine this with our own AI model. So in this case, exactly, the difference will be for the solid phase. Because usually the approach is you have the field, then you do some sieving, then you do a PSD curve, and most, the easiest problems you can model, just consider the fuel as a sphere and just model the combustion. But in those cases where you have a more complex problem, then we use the AI to really recognize the size of the particles, and also to complete the CFD with the behavior of how that shape will change while this type of material is burning and how it affects the fluid flow. So in here we run just if we turn off our AI, this would be the results for a mill inlet. So it will go like that. So you barely see any solid in this down part. But when we turn on, this is what happened. And here I gave a zoom just to show you how the trajectory is when we have this AI and properly modeling the solid phase. And this one plays a huge difference because in here it's also blocking the gas flow to go up. So it completely changed the velocity profile. And this is where this is a little bit different from the standard CFD because it completes more the realistic particle trajectories. So for this project, we did the base case, which is the standard modeling on how they were operating at the time. And then we carried out 5 what ifs. But today I will just explore the base case, the main conclusions, and the what if tree, because this was implemented. It was not a big investment, right? So it was easier to implement, and it helped them to minimize, or at least to not suffer too much with the kiln balls. And also we got a plus benefit, which was a bonus like NOx reduction. So this is the calciner. So we take the average, this more or less the same data that it's needed for the standard modeling, but we also take pictures from the fields to be able to really check that shape and consider it. And this is the base case, so how they were operating. And for the what if tree, the main modification was to take out this the mill from the bottom inlet. Then we also took out some cold air, which was coming from the transport area in here. And this, to summarize, this was the most important modifications that made the difference. So the original design of this calciner, because of its shape, it has this angle. So in here you can see the velocity profile for the tertiary air when it's coming in. And because of that shape, combined with the shape of the calcined body, you do have a sculpture in there if you want to look afterwards. So it forces the tertiary air to the back wall, and then the kiln gas is coming from the front wall. And in the end, as you can see in here, they don't mix very well. And combining that with in the bottom part where we have, this is the base case. So you have the mill coming here. So you get very low gas velocities in this region because the mill is just coming in, so it blocks the gases, and of course it accelerates the gas in the opposite wall. And this is the effect on the velocity profile when we take out this mill. So we get a more uniform velocity profile. These are the results from the measurements from the plants for the base case, and this is what we got from the modeling. And from this, besides this design effect, we understood that especially the 3D RDF were not burning properly. And we could calculate it. From this burnout, it means on the hot mill basis, it would means 0.39 unburned carbon in the hot mill. And with that, it will accelerate the SO3 cycles, then creating some build-ups. And in here you can see the effect on the temperature profile from the base case and from the what if tree. By taking out that mill, we could accelerate the combustion. So the RDF could burn much better, as you can see the effect in the temperature and also in the oxygen profile. So we could really use and consume the oxygen for the combustion. And also we could, this is the NOx profile, and then we could create these regions. If you compare in this bottom region, you can see that from the base case to the what if tree, since we kind of changed the location where the combustion was happening, then we changed the temperature profile and also the region where it was more favorable to form NOx. So we could reduce the formation of NOx in the calciner, and also we created this region where even the NOx which was formed in here, because of the conditions with temperature and low oxygen and also some volatiles, so we create the proper condition for the NOx to come back, and then we reduced NOx as well. That's what created the effect.
Yeah, I suppose what we first seen as well as one of the positive things is our SNCR dosage. Once we increased our calciner temperature to first aid with the burnout of 3D particles, we also seen a significant drop in our SNCR usage to control our start NOx. Reason being is this: at the higher calciner temperature, it's burnt off the volatiles, and we got a better NOx reburn. So it was a very welcome addition to the analysis that we put before. As we can see, our general temperature, if we can run it, maximize the calciner temperature in around 10,500 or 1,050 degrees, we can see about 25% NOx reduction, which has been really positive and a welcome addition.
Yeah, and you're probably wondering now, okay, how about the kiln balls, right? So what we also found out, completing the CFD with the AI analysis, is that the amount of the titanium that they have creates a special condition where the titanium kind of imitates the fluoride effect. So they start to have liquid phase in lower temperatures because of the amount of the titanium and that they have together. And with that, in the very beginning of the kiln, where you should not have liquid phase, right? They start to have a little bit, and the build-ups, because the SO3 cycles was going, lots of recirculations and build-ups because of the unburned fuel in the hot mill. So some slumps of these build-ups just fall in the kiln in the very beginning, and when it happens with this small quantity of liquid phase, it starts to form the ball. So when we could improve the combustion, we reduce these build-ups formation. And also, the plant could, as you can see in here, they pretty much operate. Of course, it's a normal temperature for the kiln backend, but from time to time it goes a little bit above. And with this titanium, this is enough for them to start to have this liquid phase a little bit out of the place, which is the condition. And we could find like a guidance, like a limit. So every time they go a bit above this 0.5 for the titanium, then combined with the build-ups, then it will create the kiln balls. You want to add? Is it okay? So that's mainly what we want to give you. It's like an alert, because what I'm seeing from all the projects that we do, it's like, yeah, kiln balls are complex. From time to time, we are doing our homework and thinking, okay, I'm keeping the chemistry, the basic chemistry, okay. But when we start to achieve higher TSRs and different materials comes in, and then the chemistry can be really tricky, like this titanium being too close or changing a lot the temperature for the liquid phase. And this is not something, I mean, now that we know, it's pretty obvious and not difficult to understand, but it's not something that in the routine people keep looking and checking and even having the equipment really calibrated to do this analysis. So we just wanted to leave you as a final message that be alert, and just remember that from time to time you can have kiln balls, and most of the time it will be a combination of the combustion and the chemistry. So don't look only to one end, because it's always a combination and a complex problem. And you all received a card. So if you point your mobile phone to that part, it will lead you to our platform. This is how we delivered our modeling to our customers. So, and if your mobile supported a augmented reality, then after you enter to the platform, you can point out to this, and then it will give you the calciner in augmented reality. So in case you want to explore more, you have the base case and the water Trie results in your hands to check. And that's it. Thank you all.
Thank you very much indeed for a very interesting presentation. Who's playing with the augmented reality right now? Okay. Are there any questions from the floor? David at the front here. Please give us your company name and your name. Thank you.
Yeah, this is Giovanni, still working for Micronics. No, basically, I didn't follow all the details, but my basic question was, is this chemistry related to alternative fuel usage? So the source of this titanium, in this case, or maybe in another case, is another element, but this titanium oxide was in the alternative fuels, or what was the origin?
The origin is in our raw materials, and we are in the process of identifying which is pretty much our bauxites. So we're not in the position just to eliminate our raw materials. So the path we have chosen as a result is to try and understand it more with greater analysis of it, try to identify when we are running at high periods of it, because we can't just get rid of our raw materials.
Any other questions? Robert McCaffrey?
Hi, Rob McCaffrey, Global Cement. Is the alternative way of looking at it, not necessarily the kiln ball itself, but the fact that you actually have a kind of an enlarged ring that prevents the ball from rolling out the end of the kiln, and so it just keeps on getting bigger and bigger and bigger. And so it's almost an inevitability that you will get a kiln ball without having addressed that issue, that enlarged ring.
it's a bit like, I suppose, the chicken or the egg, which comes first. Obviously, if you can control your burning zone and control your ring build-up, it will aid you in terms of the kiln ball formation. What we've found is, obviously with titanium, and it's reducing our burning zone conditions, it's enabling the ball to form quicker. We will then maybe, which we have seen in the most recent years with trialing different alternative fuels, we are maybe letting the kiln become a little bit more unstable. So then rings are collapsing, and once we see a ring collapse, we will have a kiln ball. Or it gets too big, which has happened, where it doesn't come over the ring, and we have a kiln plug-in situation. That happens. Generally, when we have these kiln balls, it's a kiln stop. We have to, on the plant, we shoot the kiln ball. There's not too many, maybe there is, you've seen it here, but we need to take a stop. We have a big gun and we shoot the balls. So it's a big, big issue for us. So in the last 2 years, we are trying our best to understand it, and I think working with Trie has helped us. There's no doubt we have had positives since we made the changes to our calciner with limited capex involved. It's definitely positive.
Oh, sorry, just one additional question, if I may. Do you ever have the opportunity to analyse the composition of the kiln ball? So if it actually is disgorged from the kiln and passes into the cooler, is there any possibility of picking up pieces of the kiln ball and determining whether or not the composition of the kiln ball is actually any different from the clinker itself?
Yes, we have, and we have analysed that in the past, and it is very much different. You would obviously, it's a lot more unburnt. Free levels will be higher. You will have a lower sulfur content. There has been several analyses on it also. Yes, that's correct.
And okay, that's great. Thank you.
In the front here.
Hi there, Marcus Brew from Monty UK. Do you think it's a problem just that's specific to titanium, or is it any other hardened alloys that you've seen the issue with, or is that?
So far, I suppose where we've come from a Breedon point of view, when we first started investigating this, we were putting it a lot. What we were getting back, should I say, was it's alternative fuels. When we first started production back in 2001, 2002, there was no alternative fuels. We still had the same issue. So in more recent years, yes, it's become more prominent. I think the calciner combustion has definitely made it worse, but it still posed the question that you just asked. It's been only in the last 6 to 8 months that we've really honed in on the titanium aspect of it. Right. It's new to us. We're trying to get a better handle on it. So our journey is nowhere near finished.
Yeah.
It's nowhere near finished. And I suppose what this has enabled us, it's given us a path, okay? You can control your processes, you can keep it as stable as possible, but there is also always that. There might be more chemical issues.
No, that's just, I think where it was coming from. I mean, obviously the feedstock has a massive variance, doesn't it? And I suppose when now that's becoming more difficult to get quality feedstock, you're going to get more instances of that.
It's continuously changing. We have identified, as I said, in our bauxites, but we can't just get rid of it.
Yeah.
There's a feasibility around everything.
Yeah. Thanks for that.
No problem.
Cheers. Thank you.
Any other questions on the floor? At the back, James. Thank you.
This is Pietro from Refratechnic. So my question is, given that the combustion chemistry has been changing significantly since higher TSR, do you think that the traditional models of process chemistry are a bit outdated? And if yes, are you working on creating new chemical models, like for coating behavior, liquid phase, and burnability? Thank you very much.
Yes, I've been modeling kiln and calciners for around 20 years now, but with AI, I just started the company 5 years ago, so we are still working on. Every day it's new discoveries on that. And it's not so easy job because even for that different chemistry, there is a lack of data. So from times to times when we check, we find in the literature or something, some different elements could cause. Most of them, it's okay, you can do some tests on the lab, but you need real data to really training the models. And from time to time, even when I find a plant or a kiln which has this data set, when you go check, the numbers are not really properly right because these are not the main elements. So, of course, the main ones, the traditional ones are well analyzed and in the lab with some routine. But like titanium and the small elements, which are not so, the quantity is not so small anymore because of the alternative fuels, then we are developing, but it's going slowly, at least slowly than I would like to because of this challenges on the data and on training. But we are on the track. Back in Brazil, I'm modeling already 7 kilns for returning, and we are going to go up to 15 kilns. So that's why from where we are getting more information and updating our models, especially for these clinker phases and liquid phase in this chemistry part. But it's just the model is being trained, so we don't have really good conclusions or something that we can have a theory finish for that.
Is there a follow-up point?
Given that the variability of the fuels at times might be very, very high, so how do you train your models? How do you train? Do you exclude outliers, or do you have a way to model also the fat tails events, so extreme events, or do you just try to do a linear regressive models and then crunch the data on the pre-asymptotic, let's say, big data?
Yeah, it's big data, totally. Linear regression does not work here because it's a very complex problem. And we have a special, we use cloud computing because we really need computer capacity, okay? And we take big data, and we have a special code just to filter the data in the beginning. Of course, we need to take out the outliers and the trash, right? Data is not always the good one. But the difference in here, in terms of data science, is that since we started with the CFD and all this experience about the process, we teach our model, we teach our machine, because it's a machine learning technique, right? So we teach about the process. So the difference is our approach, instead of just take all the data and try to find something related to the process, we first trained the model with process knowledge, and then we guide the model to start with that. And after this, at least 6 to 10 months with training in the model, then we start to change, to look at the data and see something different. So it's what we call in machine learning area, it's a process-aware model. So we kind of train the computer first for it to be able to find the chemistry and the things which are really related to the process.
Okay, that's all the time we have for questions, so please let's thank Michael Agredi and Joana Bretz once more for their excellent presentation.